All right, I think we're good. Hello, everyone. Thank you for joining our webinar series, our Sodick and Friends webinar series. This one will be hosted by RDAbbott with the help of Romkey and Nexus. And so I'll start by introducing our speakers in the presentation today. First, I'll have Craig Lustek with RDAbbott. Craig has more than 25 years of experience in process engineering, R&D, product management, and manufacturing. As an application engineer for RDAbbott, he shares his in-depth knowledge by developing technical resources and procedures, defining optimal processes and setups, and consulting with customers and training key personnel. We also have Adam Shaw with Romkey. Adam is a business development manager at Romkey Manufacturing and Design, one of the leading mold making companies in North America, and he has over 15 years of experience in the silicone industry. And then also we're joined by Nicholas Hallett. Nicholas was recently promoted to business development manager for Nexus Elastomers, and you'll be able to find all of their contact information after the presentation. I also want to introduce our Sodick team that's joining here as well. I'll start by introducing myself. My name is John McNamara, technical sales here for Sodick Injection Molding. And I cover various territories from Minnesota to the Northeast and a little bit of the Chicago area. I'll hand it off next to Bryce.
Hello, everyone. I'm Bryce Masco. Been with Sodick for a little over 2 years now. I cover the rest of Illinois, Indiana, Ohio, and New York and Pennsylvania.
Thanks, Bryce. I'll pass it off to Bennett now.
Hey guys, Bennett Howard, technical sales for Sodick on just the molding machine side. Focused on the West Coast, the Southwest, and then a portion of the Midwest, mainly Michigan and the Milwaukee area. Been with Sodick almost 9 years now. Looking forward to seeing the webinar today. Thanks, guys, for joining us.
Yeah, of course. And then I'll finally hand it off to Kohei.
Hi, everyone. I'm Kohei Shinohara. Thank you for joining this webinar. And Sodick molding machine wanted to be the area to all the injection molding expert to join and network. And this webinar is meant to do this, to spread the knowledge by expertise. And we wanted to be, all the team member wanted to be a solution provider. Please check out RDAbbott, Romkey, Nexus, and also Sodick technical information. Follow LinkedIn. We wanted to share our application knowledge and solution. So thank you for joining.
Thanks, Kohei. Before we get started, I'm going to go over a little bit about how this webinar is going to work today. A little bit different than some of our previous webinars. We actually have a pre-recorded demo at RDAbbott's facility. And so I'm going to play that video next. You're going to see the video play, and you'll have some sort of controls on your screen to like pause and all that stuff. Try to avoid doing any of that. If you do pause and get out of sync with us, there is a button that you can sync up with the presenter. And then as well as for the questions that you have while we're going through it, please submit those questions to the Q&A tab that you see on your screen. We will not be using the chat function for this, so please submit your questions to the Q&A tab. And with that, I'll just go ahead and get started on the presentation.
Hey everyone, welcome to a special Sodick and Friends webinar series here at the RDAbbott LSR Application Center, where we're going to talk with our industry experts on what it takes to put together an injection molding machine cell to manufacture silicone articles. So we're going to first start talking about the material, the liquid silicone rubber. As you can see, we have two pail kits. So we're either going to get this in 5-gallon or 55-gallon containers. And we want to look at what material we're running. So we can run general purpose, we can run optical, we can run oil bleed. It depends on the application, the call out of the material. For this application we're running, it is a Dow low temperature cure. It's a 9400-50. So the viscosity of the material is paste-like, maybe honey, Crisco. And we talk about viscosity, we talk about centipoise we measure it in. Centipoise, 1 centipoise is water. Peanut butter is about 250,000 centipoise. LSR can range anywhere from, let's say, 50,000 centipoise on some optical materials, all the way up to 4 million centipoise. And it depends on the material itself and then what kind of additives we're putting into it. So with this material usually coming clear, but then with the application we're running, we're pigmenting it. So this is the material we're looking at, and we want to see, again, what percentage of pigment we're going to dose in, and then testing, rheology, general properties of the material. How does it work for the application, hence why we select the material. And then also, why LSR? Chemically inert, bacteria resistant, odorless, also temperature flexible. We like to say upwards of around 450, 500 degrees Fahrenheit for short periods, and as low as negative 80 degrees Fahrenheit. So this is really why you're going to select a liquid silicone rubber for your application. And we talked about bringing our industry experts together to showcase the injection molding machine. I have Nick Hallett here from Nexus Elastomer Systems to explain.
Thanks, Craig. As Craig was mentioning, this is our Servomix X20. It is our 20-liter dedicated dosing pump. It is utilizing our screw pump system with our split neck technology. It is providing consistent air-free material up to the dosing system, up to the injection molding machine, up through the hoses, up into our modular mix head, where we are mixing the material with a 1-to-1 ratio. And in this instance, we are including color. So RDAbbott Blue with our color dosing valve. We have our TrueFlow Nano flow meter that is providing a consistent, accurate color amount per shot, and then providing that into the Sodick barrel for every single cycle.
Nick, thank you so much for that. It's greatly appreciated. I'm a novice at this, so why is a dosing system so important for an application like this?
The biggest thing is providing that consistent 1-to-1 ratio. That way you're optimizing your process when it comes out to consistent parts. You guys are cutting down scrap rate, you're having good parts coming out every single shot, you're cutting down on wasted material, sorry RDAbbott, but then that way it's obviously providing profitability for your company.
You also mentioned your TrueFlow Nano High Precision Flow Meter for third stream. Now we are running a pigment, RDAbbott Blue pigment, but what other kind of applications can we look at for this? Why would this be important in some applications that customers might run?
For sure, that would be for different third stream additives, for example, for drug additives that might be added for different, different medical applications. The biggest advantage to the TrueFlow Nano is the high precision accuracy that we provide with that flow meter, so that every single shot we know exactly how much, in this instance, color pigment that we are providing for every single part. So the biggest advantage is that in this instance we can cut down actually on how much color, again, sorry RDAbbott, that we can actually allow our customers to save money by cutting down on the amount of pigment that they are using.
Thank you, Nick.
Yeah.
Well, unfortunately, we can't stop the machine and tear everything apart. So Nick was gracious enough to bring some spare components in here to discuss how the Nexus system operates.
First off, as we discussed earlier, this right here is our screw pump. It is a 3-spindle screw pump, which is different than any other pumping system on the market, which is everything else is piston pumps. Because of that, it allows us to get every little bit of material out of whether it's a pail or a barrel, and cutting down on the amount of waste that your company is on every single barrel change. This right here is our modular mix head. As the material is coming in on the A and B side, we are tracking the pressure here at the pressure transducers. So that right there is providing the information back to the X20 in this instance, and providing that consistent feed pressure and feed amount for every single shot. We have built-in check valves, so we don't have any back feed of material in between each shot. And then right here, as you can see up at the mix head, we have our horizontal mixing unit. The material's coming across the static mixers, going across the top, going across the bottom, so we're getting a nice homogeneous mix before it gets into the barrel of the Sodick. This right here is a example of our True Flow Nano. So again, as we pointed out just a little bit ago, this is for our third stream additive, providing consistent feedback to our X20 for the amount of color or additive, third stream additive for every single shot.
Thanks, Nick.
Yeah.
You mentioned having a check valve at your A and B supply. Why would this be important?
For the biggest importance is not doing a feedback for a material back up into the hoses and cross-contamination for the A and B materials. If you have cross-contamination, you have curing that starts to happen, whether it's in the mix head or in your hoses. Not so fun.
Game over in that case.
Lots of cleaning.
So I also see that you have some O-rings on some of this equipment.
Yes.
Now, preventative maintenance, we understand in the industry, we can't run forever. We do have to tear down, we do have to clean. There is no magic purge compound in liquid silicone rubber.
Unfortunately.
So it is elbow grease. How often do we have to replace these seals?
So with Nexus, we recommend about once a year that you tear apart the modular mix head, give it a good cleaning, inspect the O-rings. Sometimes you can reuse them. Don't use any solvents or anything like that. Just give them a good wipe down. For the disposable static mixers, typically we just toss them. Try to clean that, takes too much time and everything. So we do, typically every time we do a cleaning, we just swap those out. For the pump system itself, same thing, maybe once a year, do a cleaning on this. In this system, we only have O-rings, so that's a big advantage from our screw system compared to the piston pumps. There's only a few O-rings in here, a few shaft seals, that's all.
Now, one thing that I've experienced being a novice is how long does it take to tear all this apart and clean on average?
On average, so without color, I would say you can have this taken apart, cleaned, and put back together as a novice within about an hour or so. With color, I would add a little more time to that, maybe an hour and a half or so. The pump system, which it would also include the flow meter, I would say also within about an hour to an hour and a half per side.
Nick, thank you for your time.
Yeah, thanks, Craig.
We talked about the material, we talked about the dosing system to get said material to our injection molding machine, but the next piece of the puzzle is the mold. I want to introduce Adam Shaw with Remke Manufacturing Design, and Adam's going to talk about the quick prototype Remke base.
Yeah, so at Remke we do our prototypes a little bit different. Lots of places will give you aluminum prototypes, and that's great to get a part to look at and hold. It kind of tells you what it is, but it doesn't replicate true production environments. So we developed a modular system where we have a cavity stack that the customer would buy, and it fits into our quick prototyping system. We construct these out of hardened steel the exact same way that we construct our production molds. So what that allows us to do is do true production testing. Think of it more of a bridge mold, where you don't actually have to buy a cold deck and everything that goes along with it.
So that's interesting, Adam, the bridge concept that I hear all the time. So you're telling me that I shouldn't utilize a hot runner to make this part? Why is it important that we utilize a valve-gated cold deck on this run?
So for us, when we're doing our prototypes, we really want to replicate a true production environment so that when we step up from this single cavity system to a 32 or a 64 drop tool, you know it's going to run. Because that cavity stack, in theory, you could swap it out and put it into a production tool and it would work as a spare. Because everything is exactly the same as it is in production. This allows us to test multiple materials. You know, like let's say a customer needs to come to your lab and run a bunch of different trials on different durometers. We can do that quickly. We can also test out our automation. You can see the end of arm tool at the top there. So, you know, you can do a hot runner tool and it might get you some quick widgets, which would be great for show and tells, but they're really not going to tell you what you need to know about the production setting and how the parts are going to run. Not going to tell you what your cycle times are going to be, things like that.
Thank you, Adam.
Yeah.
Adam, I appreciate the quick overview, but explain to me, this is an injection molding machine, but we're running LSR. How exactly does that liquid valve cold deck operate?
Yeah, so like you said, standard thermoplastic molding, you're trying to keep the material hot outside of the mold, and then you inject into a cold mold. So with LSR, flip all of that upside down, right? You want to keep your material cold and then inject it into a hot mold. The heat helps kick off the cure cycle, so it's very important to keep all of the heat out of the mold so your material doesn't cure up as you're running.
So do we use a temperature control unit, or do we want to focus on a chiller instead?
So you can do it either way. We definitely
Okay.
have customers that go both routes. A chiller's probably more preferred because you can control every press differently. Some materials might like to run a little bit hotter than other materials, so you can kind of preheat the cold deck a little bit, not heat it up so much that it cures, obviously, but some materials kick off at different temperatures, so having individual controls is definitely helpful.
And mind you, he didn't say tower water in that. So Adam, can you explain how the valve gate cold deck works?
Yeah, sure. So it's pneumatically actuated. So we have water running all throughout the mold, and we actually get water that comes down into our nozzles here, and it goes all the way to the tip at dead ends, so we get some turbulent flow there, and that really helps pull all of the heat out at the last point, because that's the most critical point there, because that is the closest to your hot mold, because this is actually where the material shoots into the cavities.
So we have a mechanical shutoff pin on here that will stop that material from flowing forward. The inserts, as Adam mentioned before, we could take this insert stack out from their quick prototype base and we could put this into a production mold. And again, Adam was gracious enough to bring some spare components with us. We have some bases here. So Adam, with this quick prototype base, as you mentioned, you can take these insert stacks off and we can actually utilize these in a production tool.
Yeah, absolutely. So we brought some here. As you can see, these are fully hardened steel inserts. They're machined the exact same way as the production tools will be machined. Again, we really want to stress that production equivalency when we're testing our prototypes to make sure things are going to work the way that we want them to work.
Okay, so I see some lines on the outside of, let's say, the rim of the part.
Yep.
What's the importance of that?
So those are actually vents. We put those in with a specialized laser that we have at Remke. We have actually proprietary systems that no one else has to put those lasers in and control it down to really, really, really fine details. As you know, one of the main problems with silicone is flash. Not something you need to worry about with thermoplastic molds, but something that you definitely have to consider when you're running LSRs. We can get flash down to the tenths of an inch. If you mismatches, can lead to flash. So these vents are very important because you need to be able to pull vacuum to get air out, and you also need to have somewhere for the volatiles to go as the curing cycle starts to kick off.
Because as we explained, with silicone rubber, we thermally expand in the cavity, and as Adam mentioned, we volatilize off our cyclics, and we need somewhere for those to go. Now, Adam, we also, in the mold itself, we are running vacuum. As you mentioned, we want to try to replicate into a production setting as best as possible. Now, I've seen lots of vacuum cord stocks. As being a novice, I've seen lots of vacuum cord stocks, but this is kind of different. Remke has a gray vacuum cord stock, but why is it important to utilize a vacuum, and how often do we have to replace this on average?
So we actually recommend replacing those when you're doing a full system PM. If you notice on this vac seal, something that some people don't think about, there's actually a little hole there. And that hole's there so that it has somewhere to compress as the mold comes under clamp. Because the way this vacuum engages, and maybe you can show this later when the tool's running, but you'll notice it'll kind of kiss off, not clamp fully, and that's that seal touches off against each other, and you pull a vacuum, right? And then once the vacuum's pulled, you'll see the mold go under full clamp, and then you're ready to inject.
So not only does Remke provide the quick prototype base and all the components involved in it, we also have in-house automation. So with this simple mold sweep we have on this application we're running, how are we removing this part, Adam?
Yeah, I'm glad you asked. So this part actually uses an injector system and a gripper system kind of in tandem, right? So as the mold opens up, it would come forward just a little bit to kind of pop the part off, and then a gripper would come down to actually grip the part gently and pull it off. But we can also do other things, right? This is, like you said, a simple up-down unit. We can also do 6-axis robots that actually mimic hand motions, like on a complex CPAP mask. Demolding those is obviously a lot more difficult than this, right? So you actually need to replicate a hand coming in to peel the part off so you don't tear. So they can be as elaborate as that. We also utilize just simple mold sweeps with a paddle wheel to knock parts out. In this setup here, we're just bulk collecting, so the parts go off the gripper, it drops it into a bucket below, would fill up, an operator would come by and remove the bucket every so often. But if you need, lots of times for medical applications, you need actual part separation so that they can tell if there's an error in the field, right? And projects get recalled, they want to know exactly what cavity that part came from to troubleshoot it into quarantine, right? So we can do separation by cavity as well. So that kind of covers what we would call our primary automation. We also do what we call secondary automation, which would be things that happen downstream from the mold, right? This could be slitting operations. It's a very common one in medical applications with duckbills. And I believe even this part, I think eventually will get slit in a medical setting. And we can do 100% automated visual inspection. You know, a lot of these customers are making millions and millions of parts. They don't have time to sit there and pay someone to go through and hand inspect everything. So we can build robust systems that'll measure actual parts and let you know if there's a problem.
So as you can see, Remke's a complete package for your needs for molding. Adam, thank you so much for your time.
Absolutely.
I'm here with Bryce, technical sales with Sodick Lustek, and Bryce is going to discuss the injection molding machine cell we have here on consignment.
Thanks, Craig. Hi, everyone. So we have a GL100 LSR series here, and it's a 28 millimeter plunger and screw, which gives us a 82 cubic centimeter barrel size. Let me talk about the injection unit here. We use a V-line injection system with a stationary screw over the plunger. So the screw is really just feeding that material down into the plunger, and when that the material is pushing that plunger back, once that plunger reaches its set position, the screw will check forward, act as a positive shutoff, and we will inject into the mold. And as well, another thing I wanted to add is we have a little bit different clamping mechanism from traditional machines. We're utilizing a center direct ram instead of a toggle, which gives us a more uniform clamping pressure when we clamp.
Thank you, Bryce.
Let's take a walk to the back of the machine and check out some of the options and auxiliaries we have installed on your GL100 LSR machine. So as far as auxiliaries, we have the Nexus pumping unit, which is supplying a consistent round of silicone to the barrel. We have the Mold Masters mold heater. Since we're molding LSR with a cold barrel, we need a hot mold. So this is also able to be controlled through our controller on the machine, connected via Euromap. Additionally, we have a bush pump and the end-of-arm tooling supplied by Remke. There's a 15 millimeter diving tip nozzle installed on the machine to interface with the Remke QP base. Additionally, we have programmable IOs, Euromap 67, a 4-channel pneumatic valve gate, an 8-channel mold cooling water manifold, and a 2-channel air ejection system.
Thanks, Bryce. So I guess my question for you, once we have this all set up for LSR, now I want to get a hold of you and we want to run thermoplastic. Is that possible?
Converting a LSR machine to thermoplastic is definitely something we can do. I would recommend that you order a machine direct from the factory, but we can assist you knowing that people have timelines to meet.
Bryce, I appreciate it. Thank you so much. Hey everyone, so we talked about the equipment needs, the injection molding machine, the dosing system, the mold, the automation, the material. Well, one of the biggest tasks now you have is once that part is designed and then the runoff. So Adam, what is Remke looking at when you get to this process?
Yeah, so we would do a very similar fill study like this, but we're probably looking at different things than you are. You're looking more at like the process and how to stabilize that. We want to see how the parts actually fill. Lots of times with parts like this, we would do a flow study, and that would give us a really good idea of the last point of fill and where an air trap might be. But It's silicone, so it doesn't always work exactly as you planned. So doing these short shot studies is a really good way of figuring out where that last point of fill is, if we need to adjust the vents on that point to let some air out, or maybe, you know, we just can't troubleshoot it with processing alone, so we might have to add an engineered dump or waste pad to it to get your process window to open up a little bit.
So setting up the fill study here, after Remke started it up, got it running, we got it here. Now we're selecting a different material, or we're adding a pigment to it. So the engineer is telling us what pigment we need at what loading percent. So now I've got to figure out at what temperature and what injection speed is the best process. And this is more of the fill study that we're looking at for liquid silicone rubber. Unfortunately, I will say this on camera, that there is no scientific molding of liquid silicone rubber like you have in thermoplastic molding. So this is the detail that you have to go into to figure out what mold temperature you need to be at, what injection speed, and seeing the difference in fill. And you know, a few differences here, as we can see, I started at 250 degrees Fahrenheit, utilizing the low temperature cure material, and then I moved up to 275. But my two categories, I have vacuum, and then I'm pulling no vacuum. So as we go through increasing just shot size, no holding pressure, we can see the difference in fill, but also the amount of air that we're pulling through that material as we're filling out.
Yeah, so we've gone through the fill study now, and the last piece of the puzzle for Remke is usually verifying where the parts are going to stick. It might seem really obvious, and maybe you have undercuts and things, but you'd be surprised at how often parts don't stick exactly where you think they're going to. And it's important, especially if you're not doing a manual unload. If you got a robot, they need to stick consistently to one side of the mold. So, you know, some things that we might do would be go back to the part manufacturer, the actual who owns the design, and maybe ask for an undercut if we can get it. And if we can't get that, we might do some light bead blasting on one side to get it to release, and maybe polish up another side to get it to stick there. That way we get consistency, and the robot's going to work every time.
So once that validation is set up, once that's taken care of, now we can add in our demolding device and let this run fully automated. And this is how it's done. Now for the fun stuff, our fill study. As we discussed with Adam, what Remke's looking for in their runoff. Now I'm bringing into my facility, what do we have to look at for a runoff? Why are we setting the temperatures, the injection speeds the way they are? Well, as we talked about the material, this is a low temperature cure grade material. So starting out at 250 degrees Fahrenheit, as well as increasing up to 275 degrees Fahrenheit. And that's actual tool steel. That's not setting and then running. I want to make sure I'm checking the tool what the temperatures are at. And this is where you're going to utilize calibrated temperature pyrometers. So different options. I've got a 60-degree probe. Well, on the face of the tool, we might not be able to use this. I don't want to scratch it. So other options are a straight probe with little springs in here. That might not scratch the surface, but you can get in there to measure properly. So we always want to make sure that whatever our tool steel is, we're staying consistent in that. We talked earlier about the chiller. Our chiller's set at 68 degrees Fahrenheit. We don't want tower water, because tower water doesn't have cooling, it just flows, so it can change throughout the day. You can run a TCU on here. Let's say you're running this application at a different temperature than the machine behind it. So that gives you that leverage of, you know, separating out your cycles and your machines from your central system itself. So already had the luxury of running this fill study. And again, what speed do we want to run at? And this is where we're looking at trying to get a baseline of, number one, from the theoretical injection volume that we calculate, where we're starting to fill the part out at. So I want to start with a low shot size, build that up from there, but also run a couple different injection speeds. What happens when we're running slower? Can we fill it faster? What kind of defects do we get? But how consistent it is. Now, mind you, this isn't one cavity. It's not a multi-cavity mold, but you might run into that in your fill study where you could have a 4, 8, 16, 32, 64, possibly 128. How is that balance? How does it fill? How fast do you have to fill? How hot does the tool have to be? And this is that measurement of rheology. When we talk about testing material and the cure curves, it's the rheology of the material. So when are we getting this material into the mold before it scorches and filling it properly and so it doesn't flash? So from there we fill, and we want good, even articles of parts. We don't want flash, we don't want defects. And this is, again, why we set this up when we do this. So again, with a system set up for vacuum, also when we panned over to look at the parts, we can see some of these parts have a lot of air, and the different fill between vacuum and no vacuum, that vacuum is pulling all atmosphere out of the cavity. So with no atmosphere in there, we have less pressure in the tool, in that cavity that we're injecting against. So the problem is, as we are volatilizing our cyclics off from the material into the tool, that vacuum is pulling them out, but it's also ripping the material through the tool. So this could hinder a balance. And this is, again, why I ran 2 different iterations, vacuum and then without vacuum, so we could see how this fill is. Most important part with starting up before you do anything, run rheology on the material. See what the cure kinetics are. If you don't have a system, the easiest way, purge some material out of your machine nozzle and wipe it on the tool. We don't need a lot, but we're just checking to make sure that that material is cross-linking. If this is still wet and it does not cure, we've got ratio issues, and we're gonna have to look into that. So as we're starting, again, I will start with no vacuum to start off. Just want to see how this is filling and the reaction of the system itself. First few shots, we don't want to run the automation yet. Again, pulling them out by hand, seeing what the part looks like, what the fill looks like, any defects. We're going to non-fill this part on purpose. We don't want to fill it all the way, and we're also not using any hold pressure whatsoever. I just want to see what the injection is doing. How fast are we injecting? How hard are we pushing that material? Remember, LSR is compressible. We like to say upwards of 7%, but we put a force behind that and push. We can compress this material a little, way past 5 to 7%. So how much is that plunger pushing back? How much pressure are we putting on the manifold? And that's something important that you always want to discuss with the mold maker. What is the max limit of that manifold? So as we're filling out, already measured from our fill study, and we can see where we're at with no vacuum and how we need to fill. So how consistent are these parts that we're filling out? And then we want to look at, okay, again, with no vacuum. This mold does run with vacuum. We're evacuating out that cavity. Remember, we're taking atmosphere out to fill. Let's start filling up. And again, do we need vacuum? That's another question. Remke ran off already. Let's see how it runs in our application. So as we run iterations, 10, 20 shots in between. Again, let the system settle out. Let things get consistent. I want to start adding hold pressure to here. So right now, my hold time is only about 0.2 seconds. And that is basically a delay just so it doesn't bounce back and it's starting to meter right away. It's a little bit of a delay before meter. So 0.2 seconds. I know my injection pressure. My max injection pressure right now is about 4,400 PSI. So let's start low. Again, small, minute adjustments with liquid silicone rubber. The material is compressible. It shears thin. So we don't want to overpack this and flash the tool over. So I'll start out with 500 PSI just at one stage. One cavity, simple part. And you can see with our injection, we're one linear stage as well. From our interval of shots and our changing in process, starting out with 0 hold pressure, 0.2 seconds of hold time. Again, just a little delay so we don't bounce and start to meter immediately. I increased the hold pressure to 500 PSI. Remember, with LSR, small adjustments. We don't want to go too large. Ran 6 shots. That's not the 20 that I said in between, but for time constraints, we were at 1.31 grams on the process that had 0 hold pressure, 1.41 grams consistently on the process that had 500 PSI of hold pressure. Again, single stage, single time. So we'll increase it up a little bit more. So we went 500 PSI. Now what I'll do is I'll adjust this up to 1000 PSI. So we run some iterations without vacuum on just our hold profile to see how this part is filling out. Now, we weren't really worried about the hold time per se. We were just worried about the hold pressure. But with no vacuum, that white around the edge, and I'm not really filling that part. That is a burn blister. So as we are utilizing vacuum in this mold, we are trying to evacuate out the atmosphere, the air that's in that cavity. That is actually air in the cavity that is superheating and exploding back into the material. So as much hold pressure as I'm adding, I'm really not filling the part out. And that's another problem because of how much back pressure is pushing against me. So as I'm going through this iteration of fill, after we did the fill study to find out shot volume, to find out consistency, you could kind of look at this as almost as a freeze study in thermoplastics. We're not utilizing hold or hold pressure for that. I want to do that with my injection velocity, injection speed. So increasing my hold pressure, I'm not really seeing a big difference. 1.44 grams, 1.47, 1.50, 1.54. In this last profile, taking the pressure up to 2000 PSI, only at 0.2 seconds, apologize. We're 1.57 to 1.59. We're bouncing. That's telling me we're inconsistent. Remember I talked about the compressibility of the material. That pressure, no matter how high that pressure is, we don't have a lot of time there. So we have to increase that time to see what happens. So right now I have my time at 0.4 seconds and my hold pressure at 1500 PSI. We're gonna run some iterations to see what this looks like. So increasing up our hold time, dropping the hold pressure a little bit, we're getting that burn blister still. And as well, the parts are not consistent. We're jumping around in weight. So, number one, this is telling me we're not going to be able to fill without defects unless we turn the vacuum on. So, for purposes of recording, there might be some feedback due to the vacuum pump running, but again, this is part of the application that we have to set up. We've added vacuum, but I've cut back on my hold time and hold pressure as we discussed. But as we can see, the burn blisters on this part are gone, and we're getting a nice uniform fill, a nice clean edge on the part. So, part looks good, weight consistent, 1.61, 1.62 grams. So we are at a full part. We can add our automation in and run fully automated on this cell. Now, remember, this isn't a true production mold. If we're gonna have large volumes on here, we're gonna have to reach back out to Remke and have them build a larger tool for manufacturing, 16, 32, possibly 64 cavity, which means bigger cell. But for this application, let's say the customer is only needing 10,000 of these. As Adam discussed, this QP base and the insert stack is production ready. It's not aluminum, this is hardened steel. So we could get 10,000 shots easily on this to make it viable for the customer. So from here, what we're gonna do is we're gonna send this off to quality. Are they happy with the part, the measurements, CPK values? Is the color okay? And we can add automation back in to make sure we're not nicking the part, removing it. We are not damaging that nipple. And again, with this part, we still need to have secondary work. So we have to post-cure it, then slit it. We don't want to slit it in mold or slit it before post-curing, because as we post-cure, we're tightening up the general properties and we're burning off more cyclics. We don't want that slit to heal back up. So there's some more work on this application, but you're close because you've got your process dialed in now. I want to thank you for your attention during this part of the Sodick and Friends webinar series. I want to thank Nick from Nexus Elastomer Systems, Adam from Remke Manufacturing Design, and as well Bryce from Sodick. Stay tuned for the next part, the Q&A session. Sodick and Friends, assemble!
Okay, well, that was great. Thanks, Craig. I apologize to everybody for our technical difficulties at the beginning, but it seems like it went off once we got it going pretty well. And so now, as Craig said, we'll get into the Q&A portion. Let me bring in Nick and Adam. And like I said, please enter your questions in the Q&A tab, and I will go through them. So I can see that we've got quite a bit in here, so I'll start at the top. Let me just go through here. Okay, here's a good one. Was that 50 millimeter centipoise when cured or when it's still liquid? I think this was towards the beginning of the webinar.
If I mentioned 9450, so that's the Shore hardness of the material.
So after it's cured?
So once after it's cured, that's the Shore hardness you're going to get. So we like to say plus or minus 5 Shore points. So it could be 45 or it could be 55. But with all silicone manufacturers in the industry, with the better technologies out there, a lot of the materials, your range is a lot shorter. So sometimes you're getting plus or minus 2 or 3 instead.
Okay. Thanks for that answer. Here's another one. Would the modular mold work for high volume production? What would the SPI mold classification be on the modular mold?
Yeah, so like I said, we build these to be production equivalent, so it'd be a class 101. Theoretically, you could get up to 1 million shots out of one of our QP systems. Probably don't want to do that just because of the cost involved and the parts would be very expensive for your customers. But yeah, it's a true production equivalent mold.
Oh, thank you. Let's keep on going here. No one has developed a scientific approach to process development using LSR. We have applied Bazzelli methods in reversing the shear rate curve. Seems to work.
Whatever you can find that works for your application within your company. I have numerous discussions with colleagues in the industry, trying to do our best to utilize again the viscosity curves of the material, the rheology, as well as mold flow analysis. Every material is different, and again, there is a shear change with the material, and that's what we have to take into effect. Say Josh Crow at Remke Manufacturing Design. Josh might set his process up a little different than mine. He might have a slower injection speed with a larger profile, hole profile than I will. But you know, again, if the measurements are the same and you're getting a consistent fill, you know, there are different ways to go about the process. But I will say, if you found a way to develop that, I would love to talk to you about it. Because I mean, again, you know, if it's proprietary to your company, understood. But you know, this is something in the industry that we discuss all the time with, you know, a thermoplastic scientific molding, but it's very difficult with silicone just because of just how much of a different animal it is.
Got it. Thank you. Here's another one. Does silicone expand or shrink in the mold?
Thermally expands in the mold. So as silicone heats up, this is why we don't, you know, as I was saying in the video, the freeze study, we're not really freezing the silicone per se. We're filling it to 95, 98%, and we're utilizing the thermal expansion of the silicone and a little bit of hold profile just to overcome the thermal expansion of the material coming back through that manifold.
Got it. Got it. Here's another good one. What are the best practices for shutdown?
So, Nick, I'll let Nick and Adam attack this as well.
So from a dosing side, we're essentially purging, you know, usually B material to get any of that catalyst out of the system, you know, out of the mix head, out of the barrel, out of the mold. And then, you know, from at least a Nexus standpoint, you know, we can leave our system in manual mode. Once we kick it into manual mode, it depressurizes itself. And, you know, in that sense, it is safe working to sit there in manual mode. A lot of companies, they do a full shutdown, which with the Nexus dosing pumps, it's just doing essentially a hard power, you know, shut off. There isn't necessarily a shutdown procedure in a way. But at least on the dosing side, that's kind of what we recommend as far as like a weekend shutdown or something like this. And then obviously definitely on a long holiday weekend, it's purging those lines, so that you don't have those lines sitting with any mixed material, you know, whether it be again in the mix head or the barrel, over a long shutdown, you know, having any concerns of losing power, losing chilling, cooling water and everything like that. But that's at least on our side.
Yeah, pretty much the same for us. You would have to purge to the cold deck so you don't get curing. What happens there?
I recommend talking to your material suppliers. Ask them what's the pot life of the material. Some of your older legacy materials, they're going to cure up a lot faster. Your newer materials that are out there, from your Schnitzus, your Vockers, your Dows, your DuPonts, your Elchems, your Vockers, Momentivs, these materials can last upwards of 72 hours. So they're formulated that we can shut them down on Friday, leave them in the system over the weekend and come back. They will restructure, it will rebound, they'll start to thicken up, but you toss away the first 5 to 10 shots, freshen up the system and start it back up and run it. But always talk to your material manufacturer about that to see if that's a possibility, so you don't come in after a long weekend and you're not solidified up.
Got it. Okay, here's another one. How much does mold texture play into part sticking? We have confirmed we are past T90 cure, yet still have issues with parts sticking together post-production when bulk packed.
So I think parts sticking back together would have less to do with surface roughness. It might play a little bit of a role, but I think that has more to do with just the nature of silicone wanting to heal back to itself when you put parts together and put them under pressure.
Gotcha. Okay, let me keep going here. Let me see. In a multi-cavity mold, does weight balance needs to be checked at fill only or after heating time?
You're going to need heating time after your fill. So with no hold profile, and this is why I always say with no hold, I just want to see what injection is doing. In a multi-cavity mold, again, I always say this to everyone, I'm a cheat code. I'm only running 1, 2, 4 cavity molds in here. But when you get into your multi-cavity molds, you want to double check what's your fill, what's your balance. Are you having one cavity running away from the others? If you go from 1/2 inch a second to 1 to 2, or however you're measuring, volumetrically per se, you always want to check that to make sure your weight is even. If you're in a multi-cavity mold and you're 95 to 98% in half the cavities and some of the other ones are only 50%, your volume is going to be completely different, and you're packing so much on the others that now they're out of tolerance while you're just coming into tolerance on the others. So this is where balance becomes very integral. So weighing that at each interval of your fill study after your heat time is definitely a must. Now, because of that impact of thermal expansion, depending on how thick that part is, the longer you have in heat time, you could see in some instances, depending on if you're running a lower temperature, that thermal expansion could take a little more effect in certain parts with a longer heat time and lower temperatures versus a higher temperature. So those are also things to look out for as well.
Gotcha. Here's another good one. For the Nexus pumping system, what are the incremental amounts you can dose consistently? Can you dose sub 1% and below for semi-transparent applications?
I dose sub 1% for. I guess I'm not understanding, Craig. Are you following on that? I guess I'm not sure
If they're
what's being asked.
maybe they're
Less than-
talking about pigments.
Yeah, less
Or
than
additive?
1% pigment.
Yeah, okay. If we're talking pigment, then yes, we would, depending on part size and things like this, that's what our color percentage is being based on. So when we're setting up the color or the third stream pigment being added to a part, it's essentially we're looking at the total part weight and everything, and then inputting the percentage of color. So if you're talking a semi-transparent, part. Yes, it would all be dependent on our shot size, our part size and everything, and then how much color percentage we are setting to that.
Okay, and then I have a follow-up on that too. So there's tank A and tank B, but where does the color get mixed in?
So the color itself is up at the mix head as we have A and B coming in. We have check valves there. It's starting to mix in the center of our mix head. The color dosing valve, which is connected to our 1 liter pressure tank or 10 liter, color pump, or even a 20 liter color pump, it is being dosed using that dosing valve, and all 3 components are starting to mix before it even gets into the horizontal static mixer. So all 3 components are getting, well mixed and everything before it even enters, the barrel, and then, in this instance, into the Sodick and everything. So it's going through the color dosing valve. If we are utilizing the TrueFlow Nano, it is moving through the TrueFlow Nano to provide that feedback to, in this instance, the X20, to, accurately count the amount of color that is being dosed into each shot. And then again, all 3 components are being mixed, homogeneously all together before entering the barrel.
Got it. Okay, I wanted to say we're getting towards the end here of the hour that was allotted. I'm going to go a little bit longer because we were started a little bit late. So for those of you who want to stick around, feel free. I'll keep it a couple more questions, but just wanted to give you guys a heads up. I have a couple good ones here. Will the full recording from this training be available after today? And I can go ahead and answer. I'll say yes. This whole webinar in full will be posted to our YouTube channel, as well as just the pre-recorded video will be on our YouTube channel as well. And you might be, obviously RDAbbott has this video as well. If you reach out to them, they could share it too. And then another one is probably good for Craig. Do you have any upcoming in-person LSR trainings?
We do. Every year we have a RDAbbott workshop. It is towards the end of August, the 25th through the 28th. This is, grouping with everyone together, bringing all the vendors in as well, different vendors in as well. Sorry, I apologize. But we also host individual training. So if you want more of a one-on-one basis, we provide customer training as well.
Got it. Good. Okay. For what situations would coatings or treatments be recommended?
I assume for the mold.
I think so, yeah.
Yeah. So you can do different mold coatings for sure. You see that a lot more, maybe not on the medical side. A lot of the medical companies kind of moved away from wanting to treat the mold surface because after so long you need to retreat, right? And that means that material is all going somewhere. So when you have highly critical medical components, they don't want any questions about what could be contaminating them. We would prefer, if we're to do like surface texturing, like I said in the video, either polishing up or roughing up a surface. That would be our first step, just to avoid another maintenance item of coating and, like I said, possible cross-contamination. But there's definitely some coatings that work, and they have applications. It just kind of depends on what you need.
Got it. Here's another good one. Let me see. Are LSR and gum stock material interchangeable on the same machine?
On the Sodick, they are. I can tell you that. On other machines, you're going to have to, again, you have to talk to the machine manufacturers about the software and what you're going to need. Gum stock is a lot higher viscosity, so you can't utilize the same screw. The flights are a lot shallower for LSR, as well as your spring-loaded non-return valve. The beauty of the Sodick machine is that you can move the conveying screw, you can move the coupling back to open up the flow for the HCR. You can use the same plunger. You just have to basically purchase a straight through nozzle, larger orifice versus what we are running on the 15mm diver for the Remke QP base.
Got it. Got it. Here's a tooling question. So on a multi-cavity tool, say 16, how much variance would be acceptable to say the tool is balanced? All within 1% to 2% of each other?
Yeah, that would be great. You probably realistically would see closer to that 5% range. We would still consider that to be acceptable.
Got it.
But there's a lot of things you can tweak. Assuming your press is set up for it, you can change the timings on the gate pins and things to get your balance where you need it to be.
Okay, good. Another one here. Are lower shore silicones harder to process than higher shore silicones? If so, what are the processing tips you can provide?
You need a nice tight mold. I will reiterate, having everyone here, Sodick, Remke, Nexus, RDAbbott, utilizing the Dow material we're utilizing. These are the industry experts, the people, the individuals in the industry that we go to, that we get support from. If you have an internal tool shop, great. But if you're new to this, going down the street to mom and pop tool shop and having them build you an LSR tool, I don't really see a lot of success stories with that. And it's due to the parallelism, the critical tolerances of the mold. So if you're starting out with running a double shore zero material or an optical, anything lower than a 50 or 40,000 centipoise viscosity, you will see some flash. You're going to see a more difficult pickup on your dosing system. So, you might have to have overflows put into the mold just due to the fact of you know, you can't get rid of the flash, or you're having defects in process. So those are things to consider again when you first start out, and making sure you reach out to the individuals in the industry that can help you out for that.
Okay. I think I'm gonna do like one or two more here, and then we can wrap it up. But this is a good one that came in. What are the benefits of the plunger injection from the Sodick machine? And I can expand on this a little bit, but Craig, do you have any
So
input?
we had the Sodick. Unfortunately, the consignment is over, but we had it for 12 months, and I will say that it is very consistent. Running this, hold on, I had this written down. So Cody is a sales support for Sodick, and when we had our open house in April, we were running that catheter tip. So the whole group you see here was present for that, and then we did the video. The total stroke on this GL100 with the 28 millimeter conveying screw and plunger, it's a total stroke of 5.3 inches. My total shot volume was 131 thousandths of an inch. I was only utilizing 2.47% of that actual stroke. And anyone that knows injection molding as well as thermoplastics, there's no resolution there. We're not even close to resolution. But Cody himself was very impressed that we were getting consistent fill shot after shot. And even Nick was looking at the dosing system again. With the Nexus, we've got a lot of data acquisition that we can look to see exactly what we're getting from pigment control of A and B, and then shot volume. And even Nick was saying for how small of a shot that was, the Nexus system was doing a heck of a job of keeping up. So that's one thing where I can say that that in my past career of doing this 27 plus years, you got to look at that resolution. And especially if you're running with a machine with a spring-loaded non-return valve, you've got to watch, because sometimes you don't have consistency, and this machine is very consistent. The whole Sodick team told me that you'll see this, and with the applications we were running and testing that I did, I will attest that this is a very consistent machine, and it is very repeatable. It was a great system to work on. I'm not giving it back. They don't know it yet, but I'm going to find a spot for it. So.
Well, thank you, Craig. I appreciate the feedback there. And I'm going to go ahead and wrap it up with this last question. How do you calculate the tonnage required for your mold in silicone?
So typically, and Craig, you can disagree or agree with this, but typically the tonnage requirement on silicone, it's all going to be overkill on the presses. It has more to do with the platen sizes, just because it's different than thermoplastics, where you really got to calculate that out, and the tonnage really matters. But usually the tonnage isn't as much of a factor as the platen size on a press.
Yeah. So we like to say 2 to 3 tons per square inch. But as Adam was saying, it's different. It's difficult because if you're running a 6x6 ASTM slab and it's 72 thousandths thick, there's not a lot of tonnage there. I can run that and get away with 5 tons. If Adam redesigned it and made it 3/8 of an inch thick, now we're going to have a problem with the thermal expansion and flashing. But as he said, with the platens, it's also depending on, how big the mold is, the size of the platens you're putting in there, what kind of shutoff do you have on that machine, and also the tool itself.
Yeah, good. Well, I'm going to go ahead and wrap it up there. I would like to thank everyone for joining today. Thank you to our presenters, Craig, Nick, and Adam. You guys did a great job answering the questions. And stay tuned for our upcoming Sodick and Friends webinars. We have a few coming up in the next couple of months. You'll be seeing email invites to those, and it'll be on LinkedIn. And again, we appreciate you guys joining. I don't know, Kohei, did you have anything you wanted to add as well?
Thank you, everybody, for joining us. And that's what I'm talking about in the beginning. This is very good place to network with expertise. So stay tuned. Thank you.
Awesome. Well, I appreciate it, guys, and thank you very much.
Thanks,
Thank you.
everyone.
Thank you.
Take care.
Thanks, John.